Good afternoon to one and all, and welcome to the Systems Classification 2 section. And myself, Dr. Ganesh Miriyala, Assistant Professor from the Department of ECE and MLR Institute of Technology. In last class, we have studied about the system classification. So, in system classification, first one it is a linear we studied, and we left over with the time variant and invariant and causal and non-causal and stable and unstable, static and dynamic, invertible and non-invertible systems. So, we will go through one by one. So, for time variant and invariant system, so for suppose, what do you mean by generally time variant and invariant? So, a system response should not depends on time t. If system response depends on time t, then the system is called time variant if it depends. So, if the same system response should not depends on, if it is not depending on the any response, then you can call it as a time invariant system. So, in mathematically, how you are going to be represent it generally. So, if I take y of t is my system response, then this y of t I am taking at t is equals to t minus t naught is one position. That means a shifting time value shifting left over by the t naught units, and same x of t is tending to the x of t minus t naught. These two cases. So, with respect to t and with respect to input. So, with respect to time is first case, and with respect to input. If you find the system responses with respect to these two specifications, time and input, if those two are equal, then you can call it as a time invariant system. If it both are not equal, then you can say it as a time variant system. So, what is that one? See, I am finding the y of t at t is equals to t minus t naught. This is one of the output we are verifying. Second one, y of t same I am evaluating with x of t which is equals to x of t minus t naught. So, two outputs we are verifying. One is y of t at t is equals to t minus t naught case, and y of t at x of t equals to x of t minus t naught. If these both are equal, then the system is time invariant system. If both are not equal, time variant systems. Understood? We are going to find a system response y of t at t equals to t minus t naught, the first case one. Case 2, we are evaluating the same output y of t for the same system at x of t equals to x of t minus t naught. We are replacing that one. So, the first case, replace wherever find t, that value that value replaced by t minus t naught. And in second case, replace x of t by x of t minus t naught. These are two cases. Just check it, and if both are equal, then we are calling it as a time variant. If not equal, time invariant. Let us take y of t is equals to x square of t. Y of t equals to x square of t. The first term, first condition I am finding y of t at t is equals to t minus t naught. So, what is output? Y of t at t equals to t minus t naught. So, it's the same y of t equals to t minus t naught means in this output you are finding t only this place. That means x square of t is there, replace t by t minus t naught. So, this is the first output. Next, y of t at same x of t is equals to x of t minus t naught. So, the same y of t, x square is there, square upper portion, leave about it. X of t is there, write x of t place lo, in t place you replace x of t, replace the x of t minus t naught instead of x of t. That means x of t minus t naught whole square. Okay. Now, look at here, x of t minus t naught square and x of t minus t naught square. These two are the equal. So, that means this system is time invariant system. If both are equal, then we are calling it as a time invariant system. So, take one more example. some y of t is equals to tan inverse of x of t. Y of t is equals to tan inverse of x of t. If this is the system response related with the y of t, then same y of t where t equals to t minus t naught. That means wherever you find the t, replace with t minus t naught. Tan inverse x of, you are find the t over there. That means I am writing t minus t naught. This is the first case. Now second case, I am writing the same y of t at x of t equals to x of t minus t naught. In this case, what you supposed to do? Wherever you find x of t, wherever you find the x of t, replace with x of t minus t naught. Same tan inverse. I find x of t over there. I need to write x of t minus t naught. X of t minus t naught. So does the both are equal? Tan inverse of x minus x of t minus t naught. Tan inverse of x of t minus t naught. Both are equal. That means it is a time invariant system. Understood? So take one more example. Y of t is equals to log of x cube of t. Y of t equals to log of x cube of t. So in this case same. Find y of t at t equals to t minus t naught. What is the output? Log x cube t minus. Where you find the t, replace t minus t naught. And second case, same y of t at x of t equals to x of t minus t naught. That means log of x cube of x of t minus t naught cube. So if you check it, both are equal, then it is also time variant system. It is also time invariant system. So check it one more. Y of t is equals to 2t into x of t. So y of t is equals to 2t into x of t. In this case, we will check whether the given system is a time variant or invariant. Same. I am writing y of t first case. I am writing the y of t where t equals to t minus t naught. Wherever I find t, I just replace t with the t minus t naught. 2 is there. Next t is there. T minus t naught is I supposed to write. Next x, t is there. T minus t naught. This is the first case. This is my first output. Next y of t at x of t equals to x of t minus t naught. That means where I'll find the x of t, I need to write the x of t minus t naught. Same 2 is there. I have to write the t is there, but I don't write the x of t minus t naught. I am not writing the t minus t naught because I am particularly replacing the x of t minus t naught with the x of t. So 2 into t as it is. Next, wherever find x of t, now I can write the x of t minus t naught. Since x of t is there, so I have to write the x of t minus t naught. But I can't write the t minus t naught over here. So if you check it, 2 into t minus t naught into x of t minus t naught is first one, and 2 into t into x of t minus t naught. So does both are equal? No, not at all. So these two are the not equal. Then we are calling it as a time variant system. These two are the time variant systems. Next, causal and non-causal systems. Causal and non-causal system means present output y of t of the system which depends on the past inputs, past outputs, next present inputs. So the output of the present system depends on past inputs, past outputs and present inputs only, then the system is causal. Or you can define that system response h of t is equal to 0 for t greater than 0. When the 0 is a present time. We always start with the 0 is a present time. Then h of t equals to 0 for t greater than 0. That means for the future times. That means we are not getting the output h of t. H of t equals to 0 for t. H of t equals to 0 for t greater than 0. That means present time. So example, see, I am writing y of 1 is defining over the time interval from minus infinity to 0 x square of t dt. X square of t dt. So what is the present time? Present time is 1. So that is the output. Present time is a 1. This is a present time. Now this output is depends on the only input over there here. It is only x of t is there, that is input. So what are the inputs we are taking? From the minus infinity time to 0. So that means we are at 1 and we are taking input from the minus infinity to 0 only. That means we are completely taking the past inputs. And hence this system y of 1 is equals to integral minus infinity to 0 x square of t dt. This is a causal system. So take the one more example. Y of 1 is equals to same integral minus infinity to 0 x square of 2t. Let us take 2 and this value also 2 only. X square of t dt. So for this case, y of 2 present time is 2. Now if I take present time is 2, if t equals to 2, then what this value? X of t. X square of 2 into 2, that means x square of 4. That means future value. This y of t which is depending on the future input. So this system y of t is equals to y of 2 is equals to minus infinity to 2 x square of 2t dt, which is a non-causal system. This is a non-causal system. I'll take y of n. If I take y of n is equals to y of n minus 2 plus y of n minus 1 plus x of n minus 1 plus x of n minus 2 plus x of n minus, sorry, it's okay, x of n. So if you take, this is a difference equation. Now n is a present time. N is a present time. Now if n is present time, n minus 2 is a past time. This is past time. This is a past. This is a past. This is a present. That means y means output. Past output. It is a past output. Past input. Here it is. This is a past input. This is a present input. So there is no future word here. It is, since y of n is not depending on the any future value, future input or future output, then this is called the causal systems. So if I define y of n is equals to y of 2n plus y of 3n plus x of n minus 1. So if you take this one as an example, the n is a present time and 2n is a future time. This is a future. This is also future. This is a past. That means output, past, future output, future output. This is a past input. So since the future word is come across this, then this system is a non-causal systems. This system is a non-causal systems. It's clear? Next one, we will move across the stable and unstable systems. Stable and unstable means, if I given a signal x of t is a bounded signal. First of all, we clear with the what is meant by bounded. X of t is a bounded signal. X of t bounded means the magnitude of this x of t must be less than infinity. Bounded word means the magnitude must be less than infinity. That means a finite value. It is a finite value. Generally, we can call it as a finite. If the magnitude of the magnitude of the any system is a finite, then we are calling it as that system is a bounded system. So we can call bounded. So if I take one system and I am giving input is x of t, that is bounded. Bounded input means, bounded means I am giving the input which is the less than infinity in general word. That means finite amplitude. This h of t will produce as the y of t obviously. Then the y of t must be bounded. That means your magnitude y of t also in less than infinity. That means finite value. So in simple statement, if a system produces for a bounded input, then bounded output, then you can call it as a system is a stable. For a bounded input, it can produce as the bounded output only. If it is not, in that case, we can call the system as a unstable. For the bounded input, if any system provides the bounded output, then the system is stable. Then if it is not, then it is a unstable. Is it clear? We'll come across with the examples. See, y of t is equals to x of t directly I am taking. Y of t equals to x of t. Then let us take x of t, as I mentioned, it must be bounded. So it must be bounded. Let us take x of t is a u of t. That means if you look at the u of t, what is the amplitude? Then amplitude is 1 only. The magnitude is magnitude of u of t equals to 1. Then what is the y of t? Y of t equals to 1 only. Y of t equals to 1 only. Or else you can take one more one. Same y of t equals to some 8 into x of t. Similarly, for the same case, if I take an x of t equals to u of t, 8 into 1, which is nothing but 8 only. This is also finite. When 1 is finite, input is 1 is finite, that means bounded, I am getting the output also finite. That means this system is a stable system. And let us take one more signal. Y of t is equals to some t into x of t. Let us take y of t equals to t into x of t. So take same input signal. As I mentioned, it is a bounded input, u of t. This is a bounded input. The magnitude of u of t must be 1, and apply the y of t equals to t into 1, which is nothing but t. So y of t equals to t you are getting. Where initially, where t tending to the infinity also, the amplitude is 1 for u of t. T tending to infinity, if you are tending to infinity, the amplitude is 1 only. Where comes to the t is a ramp function. Ramp function is looks like this. Where t tending to infinity, the value also, magnitude of t also going to be infinity. So that means y of t, which is not equal to the finite, because as a t tends to infinity, your amplitude, magnitude of y of t is getting infinity where t tends to infinity. That means the signal is, the system response is not the finite. Even though you are giving u of t equals to 1 is a finite input, at t equals to infinity also you are getting the same output, 1 only, where for the initial one, but input is output y of t, you are getting at the t tending to infinity, then magnitude of y of t you are getting it as a infinity. That means it is unbounded signal you are getting. That means y of t equals to t into x of t, whatever the signal we are, so system response we are considering, that is unstable. Give the first bounded input, then check the output. If it is bounded, then we can call it as a stable. If it is unbounded, we are calling it as unstable. Next, static and dynamic. So it's a very simple. You can call it as a static. That means memoryless. Dynamic memory system. So if a system has its memory, then it's called a dynamic system. If a system has its memory less, that is called the static system. Memory means it should store some data. That means past input, past output. If it stores the past output and input, that is called the dynamic systems, or you can call it as a memory system. It cannot store, no storage. That means it depends on only the present output, depends on only present input. So in general, if I said any system response y of t depends on only present input, then this is called static. And the same y of t depends on past and present input and past output, then that is called the dynamic systems. Example, y of t, it is a present, y of t is equals present, it is x of t plus 2. Then y of t is a present, y of t minus 2 plus x of t minus 3 plus x of t. See, y of t present time, which is completely depends on present time only present. Here y of t present, then t minus 2 past output, t minus 3 past input and t present input. That means there requires memory for these two cases. There requires the memory for these two cases, but there is no need of memory over there. This is called the static systems, and this is a dynamic. Is it clear? Come across one more example. Similarly, y of t, y of 4 integral minus infinity to 3 x of t dt. Y of 4 is a present time, so t is completely past, minus to 3, that means past data which is storing, fast data. That means the storing is only for the memory systems. That means dynamic. Is it clear? Next, invertible and non-invertible. So when a system y of t is there, which is given by x of t, like that, then if you are able to recreate your system from the input to output, output to input, then we are calling that system it as a invertible system. If you take one box, that is a system, if you given the input x of t and if you are getting the output y of t, that is, you can say h of t something is there. Then in reverse, if you give the y of t as input, you should get the x of t as output. That is called the invertible systems. In general, it is a invertible system. But what is the criteria for this one? How we can define that when the system, given system is invertible or not? Mean, we will simply take the only one function, that is the system response must be single valued function. The system response must be single valued function, then definitely we are going to get the invertible systems. Like, if, let us take, why we are calling it as a single valued function. This is the input, we can say it as a, and output is, we can take it. Let us take, I mapped input from 1, the input output relation which is given to me, it is a for suppose 4. Okay. Next, for suppose 3 is there, then this is mapped to the value, it is 9. Take it as a 2 and it is 4, and 3 mapped to 9, 8 mapped to the 64. So in this case, this 2 and 4, 3 and 9, 8 and 6, these are the only single responses. Let us take the same, this is up to 8, and 8 it is has a 64 and 8 it has a 94. For the single values, I am getting the 2 responses for this one. If I given only single value, I am getting the 2 responses for the same output. So in which case we can say it as an invertible and in which case we can say it as a non-invertible. So if I move from the 2 to 4 in this direction, that's a possibility. Then I can move from the 4 to 2. Similarly 3 to 9 and 9 to 3 and 8 to 64 and 64 to 8. But comes to 8, for this case you can move 8 to 64. 8 to 64 and similarly you will have the 8 to 94. So if I get these two cases at a time, then the system will get confused in which direction it can move. For the 64 also you should get the move to 8 and for the 94 also you should move to the 8. So this is not the single value, this is a multiple values. So in block diagram, in a graphical representation I can represent like this. So at any time interval time t equals to 1, then I have only one value for this one. This is for the single valued function. For the multi-valued I can represent like this. So for this instant time t equals to 2, I can get the how many values? 1, 2, 3, 4, 5. 5 values. So these 5 values will create the ambiguity for the system to move from the front to back and back to front. So only front to back it can move, but the back to front it is not possible. So that's why the system cannot be invertible for this case, and the system is invertible. The system is invertible for the second case. So let us take what we discussed till now. So first one we have discussed about the linear. In first lecture we discussed about the linear and non-linear, and in second one lecture we discussed about the time variant and invariant, static and dynamic, and causal and non-causal signals and systems. And in next class we are going to be discuss about the transfer function for the LTI systems, transfer function for the linear and time invariant systems.